Namaskaram to everyone. Welcome to series of lectures on finite element method. Today we'll discuss about stiffness matrix for two-noded 1D bar element using natural coordinate system. In the previous class we discussed same stiffness matrix using global coordinate system. So today we'll talk about natural coordinate system. The reason being discuss this class is in many books they discuss stiffness matrix in terms of natural coordinate systems. That's the reason we are delivering this lecture to find out stiffness matrix using natural coordinate system. So if you remember in the last class we discussed how actually this stiffness matrix comes. If when we are using the potential energy equation, we know the potential energy phi is equals to strain energy and work potential, and we will get the stiffness matrix from the strain energy part, right? So if you write this expression, we have of volume integral sigma transpose epsilon naught into dV minus of volume integral u transpose f of dV, which is a body force, minus surface integral u transpose t into ds, and sum of all the point loads uti pi. So from this expression, if you see here, from this part you will get the stiffness matrix. So from this you will get body force vector, and from this you will get traction vector, and this is basically your point loads. So we'll focus on how to find out stiffness matrix. So if you write this stiffness matrix, so I am just rewriting the strain energy is equals to half volume integral of sigma transpose into epsilon naught dV. So if you remember, we written what is actually the strain epsilon naught. Strain is nothing but your BQ, and your stress is nothing but your dBQ, where D is actually material property matrix. If you are considering for the one dimensional element, you can write that D as just Young's modulus, then we can write them as EBQ. So now once you have the values of BQ and EBQ, so both you can substitute in strain energy expression. So we'll continue with that. So we have UE that is equals to of volume integral of, now I am writing this sigma, that sigma which we got it as EBQ, this transpose into strain, that's nothing but your BQ into dV. And once we are making a transpose, if we rearrange them, we will get this one as Q transpose, and E is a material property you have, right? So we can just write it as E, B transpose and E and B and Q. So volume integral dV. And if you rearrange these terms, you will get of Q transpose into volume integral of B transpose E B dV into Q. Now this, if you see, this term is nothing but your element stiffness. How we got this element stiffness? We already discussed in a previous class. If you consider a spring which is having a stiffness K, and if you subject it to some force, then the spring will be deformed to some distance F. So from here to here, this is nothing but the displacement of the spring because of this force. And if you want to find out the strain energy in the spring, the strain energy will get it as strain energy UE in the spring is nothing but half K x square, where x is nothing but your deformation. Right. Now if we correlate these two expressions here if you can correlate these two expressions here, this QTQ is nothing but your K square. Then rest of the term, this if you see of which is common, then the rest of the term you have this Ke, that's nothing but your K. That is your stiffness of the spring. So here it is the stiffness of the element, one dimensional element which we have considered. So in this way you will get the stiffness, element stiffness K is nothing but volume integral of B transpose into E into B into dV, right? Since E is a constant and I can take it out, and this dV I can write this volume as A into dx. Since it is a one dimensional element, so the variation is there or only in x direction, so into cross sectional area of that element. So I can take it out these terms, A into E out, then I'll get this one as 0 to LE is the length of the element, that's nothing but B transpose into B into dx. So this is the expression we got for two noded one dimensional bar element. So now if you see here, it is 0 to LE dx. The dx is now it is actually in the global coordinate system, which is a Cartesian coordinate system. But now we want to write these expressions in natural coordinate system. So I have to convert this global coordinate dx into a natural coordinate. So that means we have to know the relation between the natural coordinates and the global coordinates here. And same time the limits 0 to LE, which is the length of the element. So that also we have to know it in natural coordinate system. So we will see now, if you consider the same bar element, right, which is having a node 1 at one end and node 2 at another end, right. So we know the displacement q1 here, the displacement is q2. If you take a global coordinate system, here we consider this was an x1 and this is your x2, and this is the length of the element which we have considered, right. So now if you consider that one in a natural coordinate system, so this will be a zeta minus 1 and this is zeta plus 1, and in the middle we will have zeta is equals to 0, right. So now you have to develop the relation between this zeta and global coordinate system, that which we have discussed already. If you remember, we written this zeta is equals to 2 times of x minus x1 by x2 minus x1 minus 1. Now if I differentiate it, I will get this d zeta is equals to 2 times of dx upon x2 minus x1, right. So you know what is this x2 minus x1? x2 minus x1 is nothing but the length of the element. So I can write this d zeta as 2 into dx by this length of the element. So if I write dx, I will get this one as LE by 2 into d zeta. So we got the relation between this global coordinate system and natural coordinate system. Once you know that one, that you can substitute in your previous expression which we have. Here we have an expression that is 0 to LE B transpose into B into dx. So now you replace the dx with the zetas and you change these limits from 0 to LE to minus 1 to 1, which are the values at the node 1 and node 2 for this natural coordinate system. So I will write that expression now. I am writing here, I have an expression now, strain energy element stiffness matrix K, that's nothing but A into E minus 1 to 1 and B transpose into B into, so we got this expression, this dx I can write it this LE by 2 into d zeta, right. And you know we already derived, I think, 2 classes before, but what is this B? B is nothing but your strain displacement matrix. If anybody remembers, what is the strain displacement matrix for two noded 1D element? If you don't remember, just I'll write the term, that is 1 by length of the element, 1 by length of the element. So this is your strain displacement matrix B, and if you write this B transpose, that B transpose will be minus 1 by LE and 1 by LE. So now you substitute this B and B transpose into the expression. If you substitute them, then we'll get this K is nothing but A into E minus 1 to 1, and B transpose, that is minus 1 by LE into 1 by LE into minus 1 by LE to 1 by LE into LE by 2 d zeta. So LE by 2 to d zeta. So now we converted the entire expression in terms of natural coordinates. Just multiply this 2 and LE by 2, which is again length of the element, I can take it out. So I can write this one AE into LE by 2 out and minus 1 to 1. And if you do this matrix, so now this is of the form, you have the 2 rows and 1 column. So 2 by 1, and it is 1 row 2 column. So you will get a 2 by 2 matrix, right? So if you do it, you will get minus 1 by LE multiplied with minus 1 by LE. So I will get 1 by LE square, right? So here if I do this one, minus 1 by LE, 1 by LE, so I will get this here as LE square, and again 1 by LE minus 1 by LE, so I will get minus 1 LE, same I will get LE square. So you will get this expression into d zeta. Since again 1 by LE, again it is a constant matrix, so if we can see this, we can take it out, AE LE by 2 and 1 by LE square minus 1 by LE square minus 1 by LE square 1 by LE square matrix out. So you will have this minus 1 to 1 d zeta, right? Now you substitute this zeta, if you do it, then finally you will get this expression AE LE by 2 1 by LE square minus 1 by LE square minus 1 by LE square by LE square, and you will get this zeta, and if you put the limits for this, you will have minus 1 to 1. So if you substitute the limits, you will get 1 minus of minus 1, so you will get AE LE by 2 1 by LE square minus 1 by LE square minus 1 by LE square by LE square. This you will get 1 minus of minus 1, right? So it will be 2. So this 2 will get cancelled, and here we have LE, and in this we have 1 by LE square. So I can take it out, this I can write it as AE. Okay, let me write the next, right? So I'll get this KE is equals to AE LE by 2 1 by LE square minus 1 by LE square minus 1 by LE square by LE square into 2. This 2 will get cancelled, and this LE, so I can take it out, this 1 by LE square out, so I can get this one as AE LE by LE square 1 minus 1 minus 1 1. So where this LE get cancelled, then I'll get this one as AE by LE 1 minus 1 minus 1 1. So again this is your element stiffness matrix. So this is nothing but your element stiffness matrix, where this A is nothing but cross sectional area of the element, right? And E is Young's modulus of that element, and Le is length of the element. So this way you can write the expression for element stiffness matrix for two noded one dimensional bar element. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.